Hello, today I'm going to tell you about how you can visualize something interesting with Kuibit. Kuibit is the official post-processing and visualization library for Einstein Toolkit, and today I'm going to walk you through how to visualize horizons and how to visualize some time series using Kuibit. And I'll try to guide you through this example, and hopefully it's going to be a useful learning experience. So let's get started with what is Kuibit. Actually, let's get started with what I'm planning to do today. Well, first I want to introduce Kuibit, very, very briefly and very generally. I want to also briefly set up and install Kuibit just to show you what you can do it and tell you what will be your first steps if you were to start from scratch. Finally, I want to go through an example with you and build up the example with you so that we can learn together how to do something that is interesting. But first of all, point one, what is Kuibit? Well, Kuibit is the official post-processing and visualization library for Einstein Toolkit. We define post-processing as visualization, like what we have here on the left, which is like a color map of our density for a simulation. And this is useful to get a sense of what's going on. But it's not the end of the story. When we want to do post-processing, we also want to do something that is quantitative, such as, for instance, computing gravitational waves, or we want to be able to compute variables that we didn't compute during the simulation, but we had their primitives. For instance, some combination of something that we output, but we forgot, or like to get something that we forgot to output during our simulation. And Kuibit is a Python library that allows you to do this by taking care of all the low-level details so that you can focus on the science and not be bogged down by all the technical details about files and data structures and stuff like that. So now there is already a lot of documentation about Kuibit. There's lots of tutorials. So in these tutorials, I describe Kuibit in much more details, and I specifically include this last tutorial. As you can see, is a long one. Goes over the details of Kuibit and walks you through how to get some interesting stuff done with Kuibit. So I'll encourage you to have a look at these tutorials if you're really a beginner and you don't know anything, if you want to get a sense of how to use Kuibit, we walk through the first steps, then you can follow this last tutorial. But today I would like to expand upon this video documentation and tell you more. I want to walk you through a different example. So I'm going to go quite fast in describing Kuibit and guiding you through the first steps. But I do want to emphasize that one of the key starting points in Kuibit is documentation. There's lots of documentation. There's all sorts of documentation. Documentation to tell you how the different modules are set up and why they're the way they are. Tutorials to tell you how to use those modules. There's a lengthy description of all the APIs, all the various functions, and how to use them with their signatures and so on. And there's lots and lots of examples that you can immediately use to do science, such as, I don't know, plotting 1D variables, plotting horizons, and so on. So please do look at the documentation. But of course, the documentation is not going to be comprehensive. So if you want to get to the next step, if your still documentation doesn't answer your question, then the next step is how do you get help with Kuibit? And you can, the easy answer is that you can reach out to me. You can send me an email at this email address. You can join this Telegram group with users of Kuibit, where hopefully people help each other. And finally, if you catch me around, you can definitely stop me and ask me a question at any time. I'm always thrilled to chat about Kuibit. So with that, I would like to also point out that Kuibit is published in the Journal for Open Source Software. So if you use Kuibit and you find it useful, it will be great if you also cited the paper. I once again point out that there's this Telegram group where they're used for announcements and in general for support, or you can use the email address, this email address to reach out to me. And what is Kuibit? What does it mean? Well, Kuibit is this stick here that is traditionally used by the people here in Tucson, indigenous people here in Tucson, to pluck the fruit of the saguaro cactus. So my personal slogan for Kuibit is, well, harvest the fruit of your cactus simulation with Kuibit. And before I get into more details, I would like to emphasize that Kuibit, as many great things, was built on the shoulder of giants, particular by on top of the PostCac package developed by Wolfgang Cashdown and by the amazing data science and scientific ecosystem for Python, particularly NumPy, SciPy, and H5Py. And the development of Kuibit was also supported through various grants to me or my group, particularly by NASA, the Texas Advanced Center for Computing, and National Science Foundation. Okay, this was the very, very brief introduction to Kuibit. So now, how do we get started? How do we install Kuibit? Well, here I have a couple of links that you can use to get started. Oops, sorry about that. To get started with Kuibit. And maybe we can visit the documentation. We look for Kuibit online. The first link is the documentation, and you can see there's the same link, first steps, which tells you how to install Kuibit, what is Kuibit, and walks you through some key ideas in Kuibit to hopefully guide you in using Kuibit. And I also want to point out that when you install the Einstein toolkit, or actually when you just download the Einstein toolkit, you already have part of Kuibit. Well, you have Kuibit in its entirety, but you also have all the examples, and the examples live here in Cactus, Utils, Analysis, Kuibit examples. And examples are really useful because I call them examples, but they're ready-made scripts for you to do interesting science. So with that, how do you install Kuibit? Well, on most systems, you can just use pip. Kuibit is a Python package, so you can use, let's try it on this system. I have here pip install Kuibit user because I want to install it on my partition, on my user only, upgrade. And because maybe I have an older version of Kuibit, and when I do this, well, in this case, I get an error. And here what we learn is that actually the Python ecosystem is much more complex. And in this case, I'm working on a very modern machine using very modern operating system that doesn't allow this pip. So now this is probably not going to be the case for most machines that you're working with, especially if they're Linux machines. And this command will just work. But I point this out because I want to stress that Kuibit is a very normal, traditional Python package. So if this doesn't work, just follow the instruction to install any Python package, and that will work. But of course, I have Kuibit on my computer, and there's a second step that I highly recommend when we install Kuibit. That is to add to your environmental variable path the location where the examples are live in your Einstein Toolkit installation. So as I pointed out, every time you install Einstein Toolkit, you're going to have the examples. And what this command does, it will allow you to just call from anywhere on your shell any of my examples or the examples that you have. Okay, now there's an error because I'm running stuff completely randomly. But this code that I'm calling here, it lives within this folder or some links to this folder. We can probably have a look at it. Plot sci for lambda pi. Yeah, so it lives in Kuibit examples. And so what I can do is I can run all the examples on the data for any simulation from anywhere. And I can do this because I added this line. So I think this is super useful. But again, you don't have to do that. It's completely up to you. So once again, this was a very, very, very brief introduction on how to install Kuibit and what I would recommend you to do for Kuibit. So check out the videos, check out the links, just pip install, and you can add this path to make things a little bit easier. So now we can, before we move on, I want to encourage you also to use Kuibit, but also contribute to Kuibit. I think, of course I'm biased, but I think Kuibit is a really good framework to make your codes available to the community. And the same Einstein Toolkit is a framework for you to add a new thorn that other people could use. With Kuibit, you can share your analysis, and you can give everyone access to useful tools. So Kuibit is completely openly developed, it's completely accessible, it's very well documented, very well commented, it's hopefully easy to extend, and hopefully, I think there's also some interesting stuff to learn in this, not only when it comes to contributing to open source software, but also there's, I think, interesting ideas in computer science in this package. So I highly, highly, highly encourage you to feel welcome to contribute and to feel that this is a good opportunity for you to learn if you want to learn. Okay, so with that, now again, this was my super brief introduction. And the reason it's so brief is because I think I already gave a very comprehensive introduction in my previous videos. So I want to provide more content, provide more useful information, look at things that I haven't looked in the past so that there's more material available for you to review maybe after this conference or at any time. So with that, what I want to do now is I want to walk you through an example. I want to consider a very traditional use case. That is, I want to plot like horizons. So let's do that. So now I'm in this folder here. I have a data folder. So in this data, we can look at the data folder. There's a bunch of output folders with a simulation that I performed. There's already some scripts, which are the scripts I prepared to ensure that I am able to go through this example, but we're going to ignore them. So let's create a new script. This is my way of interacting with Kuibit mostly, and we're going to plot horizon.py. Okay. Now this is a script, and what I typically do is I'm going to write my script here, and then I'm going to open REPL, which I already have. So maybe let me close this REPL, open a new REPL. So I have a Python REPL. So if I type here, the script, I can send information from the script to the REPL. And I use this as a way to interact with the system. So the first step is to import. Let me also do this so that it's a little bit cleaner. So it's to import simdir. And I hope my keyboard is not too loud. But so when we import simdir, what we do is we get access to the data. So we can create a S as a simdir. Let me call it sim. Simdir, and it's going to be in the data folder, horizon. Oh, sorry, we're not there yet. And this simdir. So if I evaluate this now, folder doesn't exist. So where am I? Okay, I don't know why, so I'm going to provide the full path. Repos, we all Kuibit horizons. Let's see. Okay, yeah. So this is the path where our data lives. Now, there's probably some issue with with my Redfield path. So here I provided the entire path where the data lives. And what I'm going to do, that is going to be useful. There's a technical detail, but I'm going to put it anywhere. I'm going to use a pickle file. So pickle file is at this stage is just a way to speed up some calculation. It's not needed actually. I mean, let's not do it. I'll do it later if we need to. Yeah, we probably don't need it. So we've done this. So what is this? Okay, sim now contains a description of what's inside this data. For us, what we really care about is horizons. So I'm going to create our horizons, sim horizons. I'm going to evaluate this, and let's see what's inside horizons. So we can, every time we can print, okay, so we found in this data, there's 3 horizons that were found from these thorns. There's no horizon from quasi-local measure. It's because they're not going to be needed here, so I didn't include them. So here we learn that there's 2 representations, or there's at least 2 representations for horizon data in Einstein Toolkit. One is the shape of the horizon as a geometrical object, and the other there's information about the physical properties. So a parent horizon finder direct finds the shape, find the horizon, and then quasi-local measure evaluates physical information. So for the plot I want to do today, we're only going to care about this. So what we do here is we're going to read the 3 horizons. And why 3? Well, so this is a binary black hole simulation. And there's the first horizon. Then, of course, there's the second horizon. And then there is a third horizon, which is when they merge and they form a remnant. So now let's evaluate this and see what we get. So now we have we can print our H1, and we find, okay, this is when it was formed, or this when it was found the first time, and here there's a note that tells me, okay, the information about the shape is available, and we want that. We want the information about the shape because we want to make a plot, a 3D plot for the horizon. So maybe we can also look, okay, this was found at 2000, and this will come back later because we'll find out that 2000 was actually a mistake. The horizon was found a little bit too late, but I'm foreshadowing. Let's not worry about that for a second. Next, well, I want to make a plot. I want to make a plot of the shape of the horizon. When? Well, so we need iteration. Iteration. We have to decide when we want to plot. So specific iteration. And for instance, we can plot iteration 1024. What we can also do is we can convert the iteration to a time. So let's do that. We're going to use this later. And to do this, what we can do is we can pick any of the three horizons, use the function shape, let's see, what is it? Shape type iteration, and give the variable iteration. So if we do this, now we can see what is time. Okay, time is 7m. So this function tells me, okay, use information about the shape to translate the iteration number into a time. And okay, now that we have that, we can start doing interesting stuff. Actually, maybe let's say what is the time to merger. Merger time is going to be approximately A3 was time found. Okay, so now that we have this, we want to plot. So let's import matplotlib. And I don't like the default values for matplotlib. So Kuibit comes with a set of defaults matplotlib, which I find import setup matplotlib, which I find a little bit more legible. So we can with this setup matplotlib anytime, and it's just going to change some default values. Okay, now we have iteration, we have time. Now let's start making some plots. For instance, a plot that we can make is the plot of the separation. So for that, we can we can import yet another function from the horizon utils module in Kuibit. And there's a function that's called exactly compute separation. So we can compute separation. We have to pass two horizons. Sep. Okay, maybe let's revalue everything. Sep. Okay, so we have a time series, and there's a Kuibit time series, and we can just do plot. And let's have a look. And this is what it looks like. So if we want to know, I don't know, what's the maximum? It's probably a maximum max. Is it max? I don't know. Yes. So we will learn a two black holes separation of 12m. Nice. Okay, now that we have the separation, we made a plot of the separation. But what I really want to do is we want to make a 3D plot. Okay, now matplotlib is not really the right tool for 3D plots, but bear with me. We're going to learn something useful. So first, I have to import axis 3D. We need this to be able to make 3D plots, and then we need to set up a figure. See figure, and I'm going to give a size, just because we want to have like a true plot and like a pick some quote unquote random values. Then we want now GIF to add subplot projection. Okay, this is going to be our axis when we're going to have our 3D plot. Then we have a second one plot, which is going to be where we put our separation. So let's start with the separation. And so we're going to do plot sep. But I want to do something a little bit nicer. So what I'm going to do is this. Because we chose a specific iteration. So what I'm going to do is this. I'm going to do, okay. I'm going to pick dull color, gray. And then what I'm going to do is I'm going to crop our separation to the specific iteration where we are right now. So here what I did, I took only like a portion of the data until my separation. And the reason I want to do this is because now I can do something that is quite cute. I can plot this as well. And then I can plot the last point. And you'll see in a second why I'm doing this. Okay, so let's separate crop. Is this wrong? So what I did here is I unpacked my time series into an X and Y. I could put T and Y, whatever, and then take in the last number. This is the size of my scatter plot. And now that I do this, what I'm going to do is I have this. Now I have my entire separation as a function of time. So probably we also want to add sep. We have, so what we have here is we have our entire separation as a function of time, And then we have the point erasure what we're looking at. And if our point was, let's do that. Maybe divide by 100. Let's put this again. So the way it looks like is that there is essentially this is a progress bar. And maybe you're seeing what we're doing here. Maybe you're seeing that what I really want to make is not a still image. What I want to make is a movie. So that's why I have this cute bar. Okay, I think we're done with the plot on the right. There's not much more. I think this is interesting, and this S is just to make the dot large. I think there's an interesting usage in which I decided to go one level beneath this object. So I use some Kuibit method, and then here this is just a NumPy object. Like we were to look at this object, and yes, this is a NumPy array. Okay, now we can focus on the more challenging, possibly more interesting horizon. So for that, let me just do something that it's I wouldn't say technical, but it's boring. I'm just going to fix the limit of the plot to be a cube, so that the view is isometric. There's no direction is stretched for no good reason. Okay, so now let's look at the horizons. Let's look at the horizon as output by apparent horizon finder direct. Okay, so the way we do that is, okay, we have h1. We can take we can get the shape of a specific iteration. And this is a bunch of numbers. Actually, how many are there? So what we have here is we have 3, but then 6. Okay, so we have a complex array that is a 3 by 6 by lots of points. Maybe we can do shape. Let's see if this works. It's a tuple, so I probably have to do shape. It's a list. Okay, well, there's a lots of yeah. Sorry about the noise. I hope my voice came through. I do remember. Yeah, I was just describing how the shape is a very complex object. Let's understand what we have here. So, well, we have a 3. I'm going to P1. I'm going to unpack them this way, and you're going to see what this means. One shape iteration. So what I did, I unpacked my. Yeah, sorry about the noise. I hope my voice came through. I do remember. Yeah, I was just describing how the shape is a very complex object. Let's understand what we have here. So, well, we have a 3. I'm going to P1. I'm going to unpack them this way, and you're going to see what this means. One shape iteration. So what I did, I unpacked my. Login. Okay. I use tuple unpacking to split my first level here into 3, XYZ, because this is what they represent. Then each one of them is a list of 6 arrays. So let's plot one just to get a sense of what would they look like. And for that, we're going to use a scatter. Is this what I call? No. Scatter plot 0, P1, Z, 0. Okay. We can. Oh, no. Probably let me do this again. Yep. Okay. Oh, well, now can I zoom in? Okay, so maybe we can do this instead. We can forget about this. And okay, so here it's quite interesting. So this is a portion of the horizon. Maybe we can plot a second one to just get a sense of what these really are. So here we plot the first one. So let me plot number 1. Let me show. Yeah, so now we learn that an horizon is represented as 6 different patches, at least by default. And the reason we do this is to essentially avoid having like a single coordinate system where we have poles, because poles are problematic for integration, for derivation, and stuff like that. So we covered our horizon in 6 different shapes, 6 different patches that cover the entire shape. If you output your data as VTK, these shapes can be merged together. You can do very interesting stuff. But here we're using the raw data from apparent horizon finder direct. So we're working directly with the shape, with the patches. So if we want to plot the entire horizon, well, we have to plot all the patches. So what we're going to do is this. We're going to, well, we have for our first horizon. We're going to need it for a second horizon as well. So let's just do it. Just get the second for the second horizon. And then I'm just going to loop over. So, well, we know it's 6. So just let's put 6. And then we had this here. Oh. Yeah, I don't know what's happening. And instead of 0, we have end. And to make things a little bit cuter, I'm going to put the color as black. 1. Okay, let's see how this looks. I'm reevaluating everything. Now we have our two horizons. And now we understand why I want to set the limits. Because when the limits are not properly set, everything looks wonky. Okay, and now it looks nice. It looks nice. We're almost there. There's something that we have to consider. That is, at some point, we're going to have our full horizon. We're going to have our merger. So this is good only if our time is before the merger time. If it's after the merger time, what we want to do is we want to do the same, but for our third horizon. So we have a 3. Okay. Okay, and I think this looks good. I think this is the plot I want to make. Now, the interesting step. Now, or maybe let's make this plot. Let's have a look at everything. Okay, this looks good. I like this. Or maybe we can add some labels if we're interested. Oh, why? I don't know why this is here. Okay, Z. Okay, let's try again, just to make sure that we like what we see. Oh, evaluate everything. Yeah, we're good. I like this. Now we have to turn this into a movie. We don't have to, but I want to turn this into a movie. And I want to show you how easy it is to turn this into a movie using the tools provided by Kuibit, particular like a separate tool called motion picture. Now, because so what motion picture does is essentially, now that we can make a frame, we can very, very easily transform this code in something slightly more complex to make this more general. What we can do is, well, yeah, I'm just opening to have a reference somewhere else. 1 second, and we're going to build towards that reference. We don't need this. Oh, sorry for the mess. Okay, so here we are. Here we are. Sorry, I'm just. Okay, what I'm going to do is I'm going to create a file that I'm going to call Moppy Horizon. I'm going to copy everything. I copied everything. And now very small changes are going to be enough to transform this into a movie. So let's do that. So first, we have to create a class. The class has to be called Moppy, which stands for Motion Picture Movie. The class has to have 3 methods. The method init, where we set up all the initialization that we might need. Then we have to have a class that is a method called getFrames, which returns a list or an iterable with the list of frames, or what do we define that as a frame? Then in our case, it's going to be an iteration. Then we have to have a makeframe method that takes 2 arguments. The first is going to be the place where we want to save our frame, and the third one is going to be a parameter that defines what is a frame. For us, an iteration. The next step is we copy all of this into into these three frame methods, putting everything that has to be run only once at the beginning. So like in the init here, I think that's it. This has to be run multiple times. And so we put everything into the init, and we make them objects that belong to the class. So we put a self in front of it, so that we can access these objects from the other methods. Second, we want to have, well, actually separation is also a shared sep, and here is going to be self. Then we want to have iterations, which is going to be just the iteration for which we have some data available. Then what are our frames? Well, our frames are just the various iterations. So we want to return an iterable that is self iterations. And we're almost there. In less than 5 minutes, we transformed our script into a much more interesting movie maker. So now we don't need this anymore. And the last step is, so this h1 becomes an self h1. We want to make sure that we close any possible figure that we had, or clear anything that we had before. So we have this. But separation becomes a self. Separation becomes self. Is on PLF is PLT. We're almost there. Self. Self. This is self. And I think the only missing step is to save the figure. So we're going to into path, and we have to close it just to keep the memory clean. I think that's it. Let's try to see if this works. Okay, once we have it, what we can do is we can call moppy. Oh, and here it's where the pickle file becomes more useful. I'm going to put it, and just because in practice it's always good to have. So what the pickle file does is, okay, if we have to work on the same data multiple times, in this case we're working on the same data for produce multiple frames, what we can do is we can use the command picklify. What picklify does, it goes over the folder and understands what's inside and create a pickle file, which is just a representation of what's inside, that it's much faster to use compared to scanning the folder each iteration. Now we have this moppy horizon. We can call moppy. Plus this moppy horizon. Let's check with help that indeed it works. Yeah, everything seems to work. And we can specify our output folder, which is going to be a video folder. And now that's it. Okay, it's not it. I think I know, because I've been returned this. Yeah, so now we are creating 9,943 frames, making 2 frames a second. It's taking a little bit too long. So instead of what I'm going to do, what I can do is this. First of all, I can clean up just to make sure. I can use all the cores I have in this machine. So in this machine, I have 8 cores, as we can see here. And I can produce, well, in theory, should be faster. Now, it's not super fast right in this very moment, because I'm also recording and everything, so it's much more expensive. It should be approximately 8 times faster. It's not, but yeah. So with Moppy, we get this awesome feature. So the awesome features, 2 features. One, we just worried about making one iteration, making one plot. And in 5 minutes, we bootstrap this plot into making an entire movie. And we can easily generalize the script to taking these as command line arguments and taking other objects or parameters as command line arguments to have this code used anywhere for any of our simulation. But to have a look at what this plot looks like, instead of another way to speed up calculation is instead of using in parallel, well, I can also use in parallel, but I can also produce one frame, I don't know, like 30. This should cut down the consumption, like the CPU consumption, by a factor of approximately 30. Indeed, now it should take only a couple of minutes. And let's look at what's the output here. What we managed to make in again in a very short amount of time. And to go over this again, so we have to have a class, Mopi movie, that defines an initialization where we put everything that it has to be used throughout the code, and everything that is used over and over takes a self. Then get frames returns a list with what we define being a frame. So for us, one frame is one iteration. So all the frames are all the iterations. And one element of this enters this iteration in here. Here we say, okay, we have iteration, and we're going to plot that iteration. So the key point here is that the iteration is used here to get the correct shape, and then it's used in the prop time here to get the correct behavior for our separation. And now Mopi motion picture is doing everything else. It's taking care of parallelization. It's taking care of is reducing the frame rate, and we can add so many more options in addition to this. And to describe again what is this pickle, since we're using the same data over and over and over, it's convenient to do some basic calculations on the data, describe what we have inside our simulations, save the information into a pickle file, which we can use with the Picklify example, or there's other ways to do that as well. And then we can read this every time for every frame. Actually, maybe this is not really needed. But in any case, I think it's good practice, especially the larger the simulation becomes, the more demanding, of course, everything is. So the pickle can save a lot of time. Okay, we're almost done. We have 20 more seconds. In the meantime, we can check that indeed our simulation, well, we have a new video folder. We can look what we have in this video folder. And yes, we have what we want to have. So let's just wait 8 more seconds. Yeah, it's working. Okay, now the frames were created, and Mopi took care of also of gluing them together. So we can have a look in the video to see that we have a video. And now we can have a look at the actual video. And this is it. I mean, it's not the previous video ever, but I think it's quite effective, considering that it took us very little amount of time to make. And maybe we can loop it so that we can discuss more feature. So here we get our behavior, we get a separation, we get the separation while the movie is running. And then what I want to point out is what I mentioned at the beginning, that I made a mistake in this code in here. So I activated looking for horizons only at time 2000. So here the black holes did merge, but I didn't have my horizon finder alert to find the horizon here. So we had to wait until 2000 when the horizon finder found, oh, actually there's a common apparent horizon. And that's it. So I think this concludes my presentation, and I want to bring this again. So once again, Kuibit is published, so if you use it, it would be great if you could cite it. Please do get in touch if you need anything, if you need help, if you want to learn more, if you want to contribute. And I hope you enjoyed this talk. I hope it wasn't too rushed. I hope it wasn't too technical, but this is recorded. So if you want to review it later, well, you can review as many times as you want. Once again, please reach out to me for anything. And with that, thank you. Bye-bye.